So in this video, we're going to look at introducing trigonometry and what that means, what those ratios are, and start to look at how we're going to use these in terms of these triangles. So starting this, regardless of which sheet of triangles you have, this is the one I'm going to go through, but I will show you my proportions and my answers for the other two sheets. But I'm going to work all the way through this sheet in particular. And like I said, I'll show you the answers for the other ones as well. So looking at these three triangles, ABE, ACF, and ADG, our first question is to explain just how we know they're similar. Well, I'm going to start, since I haven't done anything with sides yet, I'm going to just look at the angles. So I know if my triangles have at least two similar angles, or excuse me, two congruent angles, they are similar triangles. So one thing I know is that all three of these triangles share angle A. So that's one angle that is congruent in all three triangles. I also see that E, F, and G are all right angles. Well, I know every right angle in the world is 90 degrees, and it's congruent to every other right angle. So because I have angle A and then these right angles being congruent, I know that they are congruent, or excuse me, they are similar triangles by the angle-angle similarity theorem. And that's using angle A and angles E, F, and G. So because, again, these three are my right angles, every triangle has angle A. We know that they have to be similar triangles because of those two congruent angles. All right, now we're going to actually start looking at our side ratios using our X and Y coordinates for B, C, and D. So here's B. Not that you can see what I'm doing with my pencil, but you get the idea. These are single units. The scale is 1. There's nothing crazy going on. So point B is at 2, 1. So X is 2, Y is 1. For C, 1, 2, 3, 4, up 2, so that'll be 4, 2. And then for D, this is 6, 3. Now the ratio that we're constructing here is Y over X. So Y over X. So that's 1/2. 2 over 4 is 1/2. 3 over 6 is also 1/2. Why is that relationship the same for all three? Well, we have similar triangles. That relationship has to be the same for all three. That's what similar triangles are. We did a whole unit on it. But if I'm using the linear function idea to explain why this is happening, I'm going to look at the slope and talk about what's happening in terms of the slope of this line through A, B. So to get from A to B, I'm going up 1 and over 2. To get from B to C, I'm going up 1 and over 2. To get from C to D, I'm going up 1 and over 2. These are all collinear points, or they all lie on the same line. So since they're all living on this same line, they should all be related using the same slope. So line AD has a slope of 1/2. So to get from one point to the next, I'm going to use the slope using that linear function idea. With similar triangles, the proportion of our sides has to be consistent as I dilate from the smaller triangle to the middle triangle to the bigger triangle. That dilation factor has to be the same, so the proportion of the sides would have to also be the same. I'm not going to write that all out, but that's my similar triangle idea explaining why that relationship is the way it is. Now in question number 4, R is the distance from our origin point, or A, to point B, point C, and point D. So now I'm not finding a coordinate. I'm actually finding the length of AB, the length of AC, and the length of AD. So for this, my Y value was 1 for point B. But I need to find the length of AB. And I'm going to actually use Pythagorean theorem. So A squared plus B squared equals C squared. I'm going to label it R squared since that's the variable that they're using here. And if I want R all by itself, we know I take the square root of both sides. So R is going to be the square root of A squared plus B squared. This is a similar variation of the distance formula that we talked about in Math 1. This is, if you had me for Math 1, exactly how we did distance. We didn't use the distance formula, we used this. So A and B are the sides of my triangle that are connected to the right angle. So here I have a side length of 2 and a side length of 1. So R for this is going to be the square root of 2 squared plus 1 squared. 2 squared is 4. 1 squared is 1. 4 plus 1 gives me 5. So 4 plus 1, because that's 2 squared plus 1 squared. I'm going to leave these as radicals. So now I'm going to do y divided by r. I'm using my Desmos Scientific Calculator app. So y is 1, r is the square root of 5. I'm going to automatically make this a fraction in my calculator just to make my life easier. And then I'm doing 1 divided by the square root of 5. I'm going to do each line step by step instead of finding the ratio last. So this would be 0.447. We'll just do 3 decimal places. I'm going to put this off to the side for a second. So the next one is point C. So for point C, my y value was 2. So to find AC, our R value is going to be the square root of 1, 2, 3, 4. So 4 squared plus this side was 2. 4 squared is 16. 2 squared is 4. So 16 plus 4 is going to give me the square root of 20. So again, I'm going to do the same thing I did before. My numerator here is going to be 2. Denominator is going to be, the square root of 20. And I'm getting the same decimal. By this point, you should know that that's not a coincidence, right? All right, last one, AD. My R value is going to be the square root of 1, 2, 3, 4, 5, 6 squared plus 1, 2, 3 squared. 6 squared is 36. 3 squared is 9. So 36 plus 9 gives me 45. And my y value is 3. This should not surprise you, but I'm going to get the same decimal. All right. Let's think about why this is happening. If I have similar triangles, this statement that I'm about to make should sound really similar because it's the same reason that it happened before, kind of, sort of. If I have a similar triangle, the relationship or the ratio created on my original triangle should not change as I dilate my triangle, because that side relationship has to maintain that same ratio as my triangle gets bigger and bigger and bigger. So the ratio stays the same throughout the dilations that we're doing from small to middle to big triangle. Again, I'm not going to write that all out, but as long as you put something in that ballpark, you're good to go. All right, last but not least, now I'm taking the x value and r, the distance from A to B, C, or D, which we already have. So I'm going to go ahead and fill those in. And then my x values were 2, 4, and 6. Now I'm going to find these ratios. So I have 2 divided by the square root of 5, which is 0.894. And I'm not going to actually type the rest of them in. I've already done this and confirmed this. But these all end up having the same, excuse me, the same ratio. Again, the proportions of the sides on my original triangle, as I dilate to the middle triangle and the large triangle, have to maintain that same ratio proportion. The only thing that's going to change is that my side lengths are going to get bigger, but they're going to do so in relationship to that original proportion that we've found. So this is not my dilation or my scale factor. This relationship is what's happening between this horizontal piece here, the vertical piece here, or that diagonal piece. Leg, leg, hypotenuse. So I'm not looking at the scale factor with these proportions here. What I'm looking at is the ratios between legs, leg to hypotenuse, and other leg to hypotenuse. And that relationship, leg to hypotenuse, or leg to leg, is going to maintain that same relationship even if I dilate it, because my triangles are similar. So this is if you had the first triangle. Again, I'm going to show you my proportions for the other triangles just so you know you're on the right track. This was my second sheet where you have H, I, J, K on your diagonal for your different hypotenuse letterings. Now, in this case, this is a very special triangle that we're actually going to talk about later in this unit. But since the legs are identical, so 2, 2, 4, 4, 6, 6, these relationships of leg to hypotenuse are going to be the same. And then this last one, it's actually the first one just flipped. So now instead of having a base of 2 and a height of 1, I have a base of 1 and a height of 2. So again, we have similar triangles. You'll notice that these proportions here are flipped because I have flipped my x value and y value from my original table. But again, these relationships are going to be the same because leg to hypotenuse and leg to hypotenuse, we're maintaining that same relationship as we dilate our triangles. So the next thing we're going to look at, we've answered this question as we've been talking, or as I've been talking, I should say. Let me focus this a little bit better. There we go. So, is it reasonable to conclude that the ratios of the legs to the leg to hypotenuse, and the other leg to the hypotenuse would have the same relationship in those questions for any set of similar triangles? Well, yes, because the proportions of the sides to themselves or to each other has to maintain that same proportion or that same ratio through our dilation. I've said it multiple times over the past few minutes, so I'm not going to write that down verbatim, but because the way that our sides are related to begin with, that relationship has to maintain through dilation, otherwise we don't have similar triangles anymore. All right, this is where we're going to also get some new terminology. So this is called my initial side. This is where we are starting. This is our terminal side, meaning that's where we are ending. And then this here is our angle itself. This is called standard position when we're in quadrant 1. My initial side starts on my x-axis. My terminal side ends somewhere between the x-axis and the y-axis in quadrant 1. So, is it reasonable to conclude that the ratio of leg to leg, leg to hypotenuse, and other leg to hypotenuse for any triangle depend on the angle in standard position, where x is on the terminal side and r is the distance from the point wherever it may be to the origin? So remember, this is where the points were changing. So, would my ratio depend on x, y? Would it depend on where I put my coordinate point? Well, I'm going to say no, it wouldn't, because if I come back and look at that very first one we looked at, I moved my XY point from B to C to D, and those relationships were always the same. So it doesn't matter where I put the point on that terminal side because of similar triangles. So this is actually no. Because of what we know about similar triangles, similar triangles maintain the side ratios through dilations. It doesn't matter where I place that point, because I could create any variety of similar triangles along this terminal side. They're all going to have the same leg to leg, leg to hypotenuse, and other leg to hypotenuse ratios, because, don't judge my lack of straight line ability, all of these are similar triangles. They all have different XY coordinates here along my terminal side, but these three ratios are all going to be the same. So, since these ratios depend on the angle measure, my ratios depend on what this angle is, not where I place this point along this terminal side. So, the ratios depend on the angle measure, so these ratios are functions of the angles. These functions are called trigonometric functions. These are our trig functions. I'm sorry you have to write functions so many times. And each of these functions have a specific name. Each function, singular, not plural. Sorry. Theta, it's a Greek letter, but that is what we use to represent the angle measurement. So down here you have a picture. So theta is my angle here. X and Y are our legs, and R is our hypotenuse. Now, you've probably at this point in your math career seen these buttons on your calculator. It is not tan, sin, and cos or cos. It is tangent, sine, and cosine. If you say tan, sin, or cos, you will be looked at very weirdly. We do not say tan, sin, and cos. We say tangent, sine, and cosine because we are well-educated mathematicians. So, what we actually were doing in those previous triangles is writing these trigonometric proportions. We did leg to leg, leg to hypotenuse, and other leg to hypotenuse. We did that. Now, some other words that you are going to hear is adjacent and opposite. This is always going to be labeled hypotenuse because it is the hypotenuse of the triangle. Now, based on what angle we're looking at is what you will determine as opposite and adjacent. So here is my angle on the other side, or the opposite leg. This would be opposite. And because this is right next door or adjacent to the angle, we label that adjacent. All right, a couple more things we're going to look at. So I'm going to do the first two of these all the way through, and then I'm going to show you the rest of my answers, but I'm going to do a few of these all the way through so that you see what I'm doing. Now, there is some estimation involved. So for this first coordinate, it's right here. There's no estimation needed. My x value is 10, my y value is 0. Now remember, here is my theta. There it is. This is r, this is x, and this is y. So based on these here, these are what I'm using to get sine, cosine, and tangent. So sine is y over r. Y is 0, so 0 divided by, well, if this is 0, there is no y value. R and x are the same thing. So this would be 0 divided by 10. Well, 0 divided by anything is still just plain old 0. Cosine is x divided by r. Well, x and r are both 10. So that's 10 divided by 10, which is 1. And then tangent is y divided by x. 0 divided by 10. Well, that is 0. Now, you'll notice I'm going to kind of do two things at once. Down here at the bottom, it also has sine, cosine, and tangent of that same angle 0. I'm going to show you how to do this in your calculator as well. So, you'll notice I have, now again, this is the Desmos Scientific Calculator app. I have sine, cosine, and tangent listed here. So I hit whichever one I'm looking for. So the first one is sine of the angle 0, and it gives me 0. Which matches. Hooray, we did the right thing. The next one I have cosine of 0, so I'm going to hit cosine of 0. And look, I got 1. Hooray, that's what we got before. And then I'm going to hit tangent of 0, and once again, we have 0. All right, so that's if the angle is 0. This is 0 because the terminal side and the initial side are identical. Now, when we move to C, D, E, F, we're going to actually have to guesstimate a little bit and do our best to kind of judge where we are and go from there. So for C, let's see. I estimated this as 9.7 because it's not quite to 10. It's a little bit before. And I estimated my y value as 1.9. So for, I'm just going to put a column here with R. There, I knew R was 10. Now, big brain moment. This thing that's happening here is part of a circle. Since all of these points lie on the circle, guess what R is for every single one? It's 10. Because R is the radius. So anytime I'm doing a proportion with R, it's going to deal with 10. So just in case we forgot, sine of theta is y over r. Cosine of theta is x over r. And tangent of theta is y over x. So r is always going to be 10. It is the radius of this circle. Now, granted, if I gave you the whole graph, you'd see a beautiful circle where I hit 10 on each axis along the way. Anyway, I digress. So sine is y over 10. Y is 1.9. So I'm going to do 1.9 divided by 10. Anything divided by 10 is moving the decimal once, so it would be 0.19. Here I have 9.7 divided by 10 for cosine because I have x over r. Well, that gives me 0.97. And then tangent is my two legs related to each other. Y is in the numerator, so I have 1.9 divided by 9.7, which gives me 1.96. All right, so again, just to show you where I went, this is my completed table. This is based on my estimation with this quarter circle above in quadrant 1. Now, since there was some estimation involved with these, this is my caveat here. Divided by 0, that doesn't work. It's an error. It does not exist. So when I come down here, since these had some estimations involved with my x and y value, there is some human error, so my values aren't going to be exact. But you'll notice they're pretty darn close to what I have here for sine, cosine, and tangent. Again, estimation, human error, not a big deal. So the only one that's ever going to be larger than 1 is tangent. With my two side lengths, my two legs that are creating sine and cosine, they always have to be less than 1. Always, 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 always. That's a requirement for sine and cosine. All right, so super quick, last thing. I promise I won't take up too much more of your time. So I'm going to put my angle down here, just because. This is my right angle. So this would be the opposite. This would be the adjacent, and this would be the hypotenuse. If you're thinking x, y, and r again, this would be x, this would be y, this would be r. Okay? So tangent is our opposite leg over our adjacent leg. Sine is, didn't really give myself enough room, opposite over hypotenuse. And cosine is adjacent over hypotenuse. So now it's going to get a little funky because I'm giving you different angles to look at. You will only be using the angles that are not right angles. I can't use the right angle. That does not make sense because the opposite would also be the hypotenuse. No, no, no. So the sine of A. Sine is my opposite side over my hypotenuse. Well, anytime I see the hypotenuse, it doesn't matter if I'm using A or C as my angle, my hypotenuse is going to be the same. So if I'm looking at A, the opposite side of A is 3. So the ratio that represents sine of angle A is 3 over 5. Whereas if I did the sine of C, the opposite side of C is 4. So this would be 4 over my hypotenuse of 5. Cosine of A, well, here's A. Adjacent is 4. Now that should look familiar because we literally just had that proportion. So depending on what angle you're using, the sine of one angle is going to be the same as the cosine of the other angle because I'm using the same side relationship, or excuse me, the same sides for these different relationships. So the cosine of C, adjacent here is now 3. So sine and cosine of A and C are the same, just opposites. It's cool. Come on, just go with it. All right, tangent of A is the opposite side over the adjacent side. So the opposite side from A is 3. That's my numerator. The adjacent side is 4. Now for the tangent of C, it's not going to be the same as this. It's going to be the other way around because the opposite of C is 4 and the adjacent of C is 3. And last but not least, here are some ratios. I have to figure out if it's sine, cosine, or tangent of angle A for 7 and 8. So here I'm using angle A. Here I'm using, oops, this is supposed to say angle C. Sorry, everybody. Typo, might be. All right, so angle A. Here's angle A. 16 is the opposite of A, and 30 is the adjacent of A. So opposite over adjacent, this is tangent of angle A. All right, now again, looking at A, 30 is adjacent. 34 is the hypotenuse. Adjacent over hypotenuse is cosine. Now I'm looking at angle C. I am no longer looking at angle A. So, in relation to C, 30 is the opposite. 34 is the hypotenuse. Opposite over hypotenuse is sine, and it's now angle C because I'm looking at angle C, not angle A. And last but not least, 16 is adjacent. Oops, if I could spell. And 34 is still the hypotenuse, and that would be cosine of angle C.